So we've been looking a lot at measures of center of a data set, the mean, the median. So here I want us to just kind of consider a little scenario up here. Suppose that you want to measure the accuracy of a GPS system that's been developed. And so you're doing that by looking at the coordinates the GPS reads out and comparing them to the known coordinates. Now, if you were to take all the readings that GPS makes and essentially average them out, that would not really be enough to say that the GPS is working, right? Because, if you have this location and, it reads here and it reads here, and maybe it reads here and it reads here, and that sort of thing. If it's kind of missing all over the place, it's possible that they could kind of average out to the correct GPS location, right? So we need to not just focus on measures of center, we also need to understand what kind of variation there is in our data. And so that brings us to this definition down here. So first of all, the deviation from the mean. So the deviation from the mean is something that I can compute for each individual data value. Okay, and so remember that X is just going to represent an individual data value, right? One data value. And this is, of course, represents the sample mean. So we're literally just saying, like, what's the difference between our data value and the sample mean? All right, and we can compute that for every single data value. And that'll give us a sense for each data value, how far off from average is it. And then if you've got a lot of large numbers, relative to the size of those numbers, when you compute the deviation, you know that there's quite a bit of variation in the data, right? It's kind of spread out from the mean quite a bit. Whereas a smaller set of numbers, values that are smaller in all those calculations you make indicate less spread. But it would sure be nice if instead of having to compute this for every single data value and try to glean some sort of meaning from that, if we could boil it down to one single number that could kind of give us a sense of how much variation there's in the data. And that is the purpose of this calculation down here we refer to as the standard deviation. All right. So what you're doing is you're taking all those deviations from the mean, you are squaring them. Remember, this means to add up, and you're dividing by one less than the sample size and then taking its square root. So kind of a lot of pieces to this. First of all, I think what I'll just say is the reason we square it is because if you had one data value that is off by 3 on the high side and another data value that's off by 3 from the average on the low side, plus 3 and minus 3 would cancel out, right? And so you wouldn't want to add those up as both positives and negatives because they can kind of cancel each other. So we square things to make sure that they're all positive. So the best thing to do is just do an example with a small data set here so we can see how this works. So they want us to find the standard deviation of this data set here. And of course, in the formula, you see the sample mean, right? So we know we've got to start by computing that. So we have 6 plus 10 plus 13 plus 11 plus 12 plus 8 all over 6, which gives me 60 over 6, which gives me 10. So my sample mean is 10. And once I know that sample mean, then I can compute the deviation from the mean for every single one of those data values. So I'll do that over here. So we've got 6 minus 10 is -4. 10 minus 10 is 0. 13 minus 10 is 3. 11 minus 10 is 1. 12 minus 10 is 2. And 8 minus 10 is -2. All right, so we did just this part, right? This inside part here. And notice we're kind of working from the inside out. Remember your order of operations, right? PEMDAS, remember that from long ago. P stands for parentheses, so we're doing what's inside the parentheses first. Then remember E stands for exponents, so we have this exponent of 2, so that'll be our next step. So for every one of those data values, we need to square this. And so remember, if you square a -4, it's -4 times itself, which gives you +16. All right, so there's all our squared deviations from the mean. And so now I'm just going to kind of put the rest of this together a step at a time. So now I want to add up all those squares. So 16 plus 0, plus 9 plus 1, plus 4, plus 4. And when I do that, I get 34. Then I need to divide by 1 less than the sample size. Now, let's just kind of pause for a moment here. Understand kind of what we're doing. Okay, I'm talking kind of loosely here. But we calculated all these deviations. We squared them. So, and then we added them up. And so when I divide by n minus 1, the reason there's an n minus 1, there's kind of an interesting one. I'm not going to get into that now. But you're almost dividing by n, right? Just like here, we divided by the number of values. So we're going to be dividing by 5 here. So we're essentially kind of doing an average type thing, right, with these squares of deviations. And so that's why, so, you know, this whole standard deviation thing is, it's not an average, don't get me wrong, but it's kind of trying to do that sort of thing in order to give us our single number that can kind of represent the amount of variation in the data set. So this is 34 over n minus 1 is 5, right, since n equals 6. So we get 6.8, and so of course the last thing is just to add that big square root there. All right, so what does this number 2.61 mean? Well, as the quarter goes on, we'll be able to attach more and more meaning to it. So it's a little bit tough to be able to say right now, okay, exactly what 2.61 tells us. But we will, on the next page, I think not the next example, but the one after that, kind of start to see how this standard deviation number is used. But before we get to that example, I do want to look at this with a larger data set, okay? In this larger data set, I don't want, personally, and I don't want you to have to go through this entire process when there are, in this case, 20 different data values. So we're going to talk about how we can use technology to help us here. So what's happening is we've got the waiting time between ordering and receiving coffee for 20 customers of some sort of coffee shop. So that's what the data represents. So we want to find a number of things, right? They ask us for the mean, for the median, for the standard deviation. They also want us to create a box plot. Okay, so there's lots of things they want us to do here. So what we're going to do is go to Stats Cloud. Now Stats Cloud is going to be kind of our main technology for the quarter. You're going to do a number of assignments on it, and you're going to get pretty well acquainted with how to use it to tell you things about data sets. So you'll have much more instruction on it to come, but for now, what I want to just do is show you how you can basically just use it as a calculator. And so remember, StatsCloud is just right here in the important class links and documents. So just open that up, click on that, and click Go to App. And it takes you to this. So if you've used Microsoft Excel before or Google Sheets, it's the same sort of a setup. So what we're going to do is just in this first column here, we're going to type all those data values. So click on that, 40. I'm just hitting enter after each one and it takes me to the next row. And whenever you're typing data in, you know, at the very end, make sure you kind of give it a once over. It's easy to, like, as you're typing these in quickly, you know, to miss a key or something like that, and then you'll wonder why you're not getting the right answer on something when it's just a simple typo. So always be careful with that. All right, so there's our 20 values. One thing I'll just say is you can name your variable. So let's just go ahead and do that. So these were wait times, right? And they were measured in seconds. Let's say seconds. Okay. And if you have a variable that has a longer name, you can always, you know, do that, make more space. All right, so here's a nice thing about StatsCloud. It does pretty much all those things that I just asked us to do, does it for us, right? So I just have to click down here, and where I clicked, sorry, I did that kind of quickly, is every time you have a variable, down here it will say mean, or maybe some other type of measurement. But down here is just, this is all the summary statistics that it computes automatically for what you put in. So if you click on that, not only does it give you the mean, but it gives you lots and lots of other things. So we can see here that we have our standard deviation, and we have our mean, we have our median, we have our minimum and our maximum, or our low and our high. So lots and lots of stuff here. So what we're going to just do here is I'm going to snap a picture of this. So we can go back to our slideshow and then use what we need. All right, let's minimize that. Let's get our PowerPoint back. There we go. Oh, sorry, I forgot to actually paste it, didn't I? There we go. That's better. All right, so we have all that information there. So we want to list all these things that they asked us for, and most of it's just right here in front of us. So we've got the mean, right? And that's equal to 117.25. It asks for, I'm going to do the standard deviation next. Standard deviation. All right, and that's over here at 42.565. Okay, and then it wants a box plot, right? So remember, with a box plot, we're going to need 5 numbers, right? We need the low, we need the first quartile, we need the second quartile, the third quartile, and the high. And of course, the second quartile we know is our median, right? So that's 115. The low is 40. The high is 200. So the only thing they're not giving us right now are our first quartile and our third quartile. Remember, the 25th and 75th percentile. But we have a way around that. So I'm going to put a little note up here. Note that that quartile 1 is the median for the first half of the data. Right? It's the 25th percentile. So it's halfway between the low and the median. So that it is the median for the first half of the data. Q2 is the median for the second half of the data. Okay, so what we can do, this is a nice little trick, is just to go back to our data set, which we'll do here. And if the first quartile is the median of the first half, then let's just take the first 10 wait times, and I just hit copy and paste and put those in one column. And then let's put the second 10 in its own column. So now, see these two new variables, and we'll just call this first half and second half of the data. So if I go down here, I can see my summary statistics here. So if I click on this, then the median of 87.5 has to be the first quartile. And if I click on this one, the median of 150 has to be the third quartile. So that's just a little way around it. So this thing does pretty much everything for you. Doesn't necessarily give you the first and third quartiles, but we have a slick way around that. Find the median of the first half and the median of the second half, and you've got it. Okay, so let's see, I'm going to delete this so I have room to actually make my plot here. And get this show started again. Swap those. Okay, shouldn't have done all those circles, now those are in the way. That's all right though. We'll just make our box plot in a different color. And so remember, whenever we're making box plots, we want to think about you know, what kind of values we ultimately need to have showing. Okay, so we have to get ourselves from 40 up to 200. We know that, so we can start here at 40. And if I've got to get all the way up to 200, that's a fair amount of the way up there. So I'm thinking let's count by 20s. So 60, 80, 100, 120, 140, 160, 180, and 200. And, oh, sorry, I forgot to actually go in and write what my first and third quartile were that we found. And so remember, the first quartile was 87.5, and the third quartile was 150. All right, so we've done this a couple of times now, so I can just go in and approximate where these are at. So we have a median of 115, yeah, it puts me right about there. We have a first quartile of 87.5, so there's 90, right? So maybe right about there. And then a third quartile of 150, which puts me right there. And then, of course, we can extend down to our low and extend up to our high. Definitely no outliers here, right? The low of 40 and the high of 200 isn't far from the bulk of the data. So we just extend the arms out in both directions. All right. Now, just to give a little bit of meaning to this idea of standard deviation that we're discussing, um, suppose I have two different tests that both had a mean score of 76%. Okay. So, test 1 and test 2, okay, both had a mean of 76%. But their standard deviations were different. So test number 1 had a standard deviation of 13, and test number 2 had a standard deviation of 7. So the questions I want to ask are, which of the tests likely had more A grades, and which of the tests likely had more C grades? So same average, right? But one of the things that standard deviation really help us with is it can help us compare to other data sets. The fact that this one is higher than this one means that there is more variation from the average, right? More variation from the average than test 2. Okay? And of course the average is, about a C, right? So what we can say here is if this means there's more variation in the average than test 2, then we can say test 1 likely has more A grades because it has more variation from the average, which is a C. Okay? But which of them likely has more C grades, right? Test 2 likely has more C grades because it has less variation from the average. Than test 1. So the fact that here we're getting a smaller number means the data is going to tend to be more tightly grouped around the average. So in here you're probably getting more C's, B's, D's, things like that, things that are close to a C, and maybe fewer A's or F's. And it's worth saying here that the standard deviation of 13 also could be due to lots more F's as well, right? And likely both. So it just, this is kind of gives you a sense of, okay, here's what we're doing when we compute this standard deviation. It helps us start to make comparisons, and we're going to be doing this sort of thing quite a bit throughout the quarter. All right, last little topic for this video. So we're going to be looking at when we take numerical data, right? We've, for a few videos in a row here, been really focusing on numerical data. So now we're going to be taking numerical data and looking at it when it's paired up with another numerical variable. Okay? So we're going to literally be looking at ordered pairs, like x, y, where both x and y are numerical variables. When that happens, what we tend to want to do is create what's called a scatter plot, okay, or a scatter diagram. So we have x and y, and we know that ordered pairs can be put on a graph. We can just plot them on an xy axis, and so this is what a scatter diagram is. Okay, so that's going to be the main visual way that we're going to represent two numerical variables that are paired up together. And so x will always, put on the horizontal axis like you're used to, y on the vertical. All right, now a little definition here is when two variables show some connection to one another, we call them associated with one another. Or sometimes we call them dependent variables. So this kind of goes back to our conversation before about, we want to be careful about using the word cause, right? An increase in x, we can't necessarily say causes an increase or decrease in y, if we're not conducting a randomized experiment, right? We had that kind of discussion before when we were talking about observational studies and experiments. So it's that same word associated with that we said was appropriate back there. We could say a change in x is associated with a particular change in y. That's okay in an observational study because you're not claiming one thing causes another. So it's that same idea of having associated variables. All right. Now, if two variables are not associated, and you can't see a relationship between them, then they're called independent of one another. All right, so let's do just an example here to kind of get a handle on what's happening. It says in the year 2000, 2,025 elementary schools were sampled to determine each school's passage rate on the 4th grade reading proficiency test, as well as each school's poverty level. And they made this big scatter plot here. So the first thing is, what does each dot represent? Well, we can figure out what each dot represents just by reading the labels, right? So X is the percentage of students eligible for free and reduced lunches, okay? And at first you might say, well, that's not really what they talked about up here. But of course what they did is they talked about poverty level, right? And so what they're doing is using students eligible for free and reduced lunch as a proxy for poverty level, because whether a student is eligible for free and reduced lunch has to do with family income, okay? So, and then over here, the percentage of students who pass the reading proficiency test, right? So each dot represents on the one hand, you could just keep it real simple. You could say a school, right? Each dot is a school, but also it tells the percent of students on free and reduced lunch. And the percent of students who pass the reading proficiency. Reading proficiency test. All right, so that's what each dot tells us about that particular school. Now part B says, does there appear to be an association between the two variables that make up each dot? Is it a positive or negative association? Okay, so deciding whether there's an association or not, it has to do with saying, can I make predictions? So if you tell me the percent of students on free and reduced lunch, can I make a prediction for you about the percentage of students who pass the test? Well, yes and no, right? There is clearly this pattern that the higher the level of poverty is, the lower the percent passing the test tends to be. However, there's lots of variation, right? So if you told me that it's 80%, here's a value way down here for an 80% free and reduced lunch, and there's a value way up here. So there's lots of variety, but if we can establish that there's a definite pattern to the data, and in this case, the pattern, if you want to draw a line through it, which later on we will in these things, draw a line through it, it would be a line with a negative slope. Then we can say there is a negative association. And that's because of the negative slope. Right, and just to kind of dust off the cobwebs of algebra class, right, why is it a negative slope? Because as you go positive in the x, you had to go negative in the y to get from here to here, right? So down a certain amount and positive that much, right? Remember, change in y over change in x, right? So if that's negative and that's positive, then you get, of course, get a negative. All right, so we're going to delve much more deeply into the topic of paired numerical data toward the end of the quarter, but we'll do a little bit with it in chapter 1 here. So this will give you just a quick introduction to that.